Plasma is one of the four fundamental states of matter, the others being solid, liquid, and gas. A plasma has properties unlike those of the other states. A plasma can be created by heating a gas or subjecting it to a strong electromagnetic field applied with a laser or microwave generator. This decreases or increases the number of electrons, creating positive or negative charged particles called ions, and is accompanied by the dissociation of molecular bonds, if present. The presence of a significant number of charge carriers makes plasma electrically conductive so that it responds strongly to electromagnetic fields. Like gas, plasma does not have a definite shape or a definite volume unless enclosed in a container. Unlike gas, under the influence of a magnetic field, it may form structures such as filaments, beams and double layers. Plasma is the most abundant form of ordinary matter in the universe, most of which is in the rarefied intergalactic regions, particularly the intracluster medium, and in stars, including the Sun. A common form of plasmas on Earth is seen in neon signs. Much of the understanding of plasmas has come from the pursuit of controlled nuclear fusion and fusion power, for which plasma physics provides the scientific basis. Properties and parameters. Definition: plasma is loosely described as an electrically neutral medium of unbound positive and negative particles. It is important to note that although they are unbound, these particles are not free, in the sense of not experiencing forces. When the charges move, they generate electric currents with magnetic fields, and as a result, they are affected by each other's fields. This governs their collective behavior with many degrees of freedom. A definition can have three criteria. The plasma approximation. Charged particles must be close enough together that each particle influences many nearby charged particles, rather than just interacting with the closest particle. The plasma approximation is valid when the number of charge carriers within the sphere of influence of a particular particle is higher than unity to provide collective behavior of the charged particles. The average number of particles in the Debye sphere is given by the plasma parameter, lambda. Bulk interactions. The Debye screening length is short compared to the physical size of the plasma. This criterion means that interactions in the bulk of the plasma are more important than those at its edges, where boundary effects may take place. When this criterion is satisfied, the plasma is quasi-neutral. Plasma frequency. The electron plasma frequency is large compared to the electron-neutral collision frequency. When this condition is valid, electrostatic interactions dominate over the processes of ordinary gas kinetics. Ranges of parameters. Plasma parameters can take on values varying by many orders of magnitude, but the properties of plasmas with apparently disparate parameters may be very similar. The following chart considers only conventional atomic plasmas and not exotic phenomena like quark-gluon plasmas. Degree of ionization. For plasma to exist, ionization is necessary. The term plasma density by itself usually refers to the electron density, that is, the number of free electrons per unit volume. The degree of ionization of a plasma is the proportion of atoms that have lost or gained electrons, and is controlled mostly by the temperature. Even a partially ionized gas in which as little as 1% of the particles are ionized can have the characteristics of a plasma. The degree of ionization is defined as where is the number density of ions and is the number density of neutral atoms. The electron density is related to this by the average charge state of the ions through where is the number density of electrons. Temperatures. Plasma temperature is commonly measured in kelvins or electron volts and is, informally, a measure of the thermal kinetic energy per particle. Very high temperatures are usually needed to sustain ionization, which is a defining feature of a plasma. The degree of plasma ionization is determined by the electron temperature relative to the ionization energy, in a relationship called the Sahara equation. At low temperatures, ions and electrons tend to recombine into bound states, atoms, and the plasma will eventually become a gas. In most cases, the electrons are close enough to thermal equilibrium that their temperature is relatively well defined, even when there is a significant deviation from a Maxwellian energy distribution function, for example, due to UV radiation, energetic particles, or strong electric fields. Because of the large difference in mass, the electrons come to thermodynamic equilibrium amongst themselves much faster than they come into equilibrium with the ions or neutral atoms. For this reason, the ion temperature may be very different from the electron temperature. This is especially common in weakly ionized technological plasmas, where the ions are often near the ambient temperature. Thermal versus non-thermal plasmas based on the relative temperatures of the electrons, ions and neutrals. Plasmas are classified as thermal or non-thermal. Thermal plasmas have electrons and the heavy particles at the same temperature, i.e., they are in thermal equilibrium with each other. Non-thermal plasmas, on the other hand, have the ions and neutrals at a much lower temperature, whereas electrons are much hotter. Of the gas, molecules are ionized, but other definitions of the terms hot plasma and cold plasma are common. Even in a cold plasma, the electron temperature is still typically several thousand degrees Celsius. Plasmas utilized in plasma technology are usually cold plasmas in the sense that only a small fraction of the gas molecules are ionized. Plasma potential. Since plasmas are very good electrical conductors, electric potentials play an important role. The potential as it exists on average in the space between charged particles, independent of the question of how it can be measured, is called the plasma potential, or the space potential. If an electrode is inserted into a plasma, its potential will generally lie considerably below the plasma potential due to what is termed a Debye sheath. The good electrical conductivity of plasmas makes their electric fields very small. This results in the important concept of quasi neutrality, which says the density of negative charges is approximately equal to the density of positive charges over large volumes of the plasma, and is not affected by Debye shielding. Comparison of plasma and gas phases. Plasma is often called the fourth state of matter after solid, liquids and gases. It is distinct from these and other lower energy states of matter, although it is closely related to the gas phase in that it also has no definite form or volume. It differs in a number of ways, including the following. Common plasmas. Plasmas are by far the most common phase of ordinary matter in the universe, both by mass and by volume. Essentially, all of the visible light from space comes from stars, which are plasmas with a temperature such that they radiate strongly at visible wavelengths. Most of the ordinary matter in the universe, however, is found in the intergalactic medium, which is also a plasma, but much hotter, so that it radiates primarily as X-rays. In 1937, Hannes Alfvén argued that if plasma pervaded the universe, it could then carry electric currents capable of generating a galactic magnetic field. After winning the Nobel Prize, he emphasized that, in order to understand the phenomena in a certain plasma region, it is necessary to map not only the magnetic but also the electric field and the electric currents. Space is filled with a network of currents which transfer energy and momentum over large or very large distances. The currents often pinch to filamentary or surface currents. The latter are likely to give space, as also interstellar and intergalactic space, a cellular structure. By contrast, the current scientific consensus is that about 96% of the total energy density in the universe is not plasma or any other form of ordinary matter, but a combination of cold dark matter and dark energy. Our Sun, and all stars, are made of plasma. Much of interstellar space is filled with a plasma, albeit a very sparse one, and intergalactic space too. Even black holes, which are not directly visible, are thought to be fueled by accreting ionizing matter, and they are associated with astrophysical jets of luminous ejected plasma, such as M87's jet that extends 5,000 light-years. In our solar system, interplanetary space is filled with the plasma of the solar wind that extends from the Sun out to the heliopause. However, the density of ordinary matter is much higher than average and much higher than that of either dark matter or dark energy. The planet Jupiter accounts for most of the non-plasma, only about 0.1% of the mass and 10–15% of the volume within the orbit of Pluto. Dust and small grains within a plasma will also pick up a net negative charge, so that they in turn may act like a very heavy negative ion component of the plasma.